Okay, this presentation on the derivatives of the trigonometric functions will be a little bit different than the presentations that we've seen so far. First of all, we're no longer talking about derivatives of abstractly given functions like abstract products, abstract quotients, abstract compositions, but instead we're talking about derivatives of individual functions, the sine function, the cosine function, and the tangent function. The other thing, and that is intentional, is that this presentation will be a bit thinner on examples than the other ones because basically you have all the tools to put these things together. We've talked about the applications of the derivative, we talked about the graphing, the increasing, decreasing, the optimization, the tangent lines, and all that. So in this presentation, we're just going to focus on how to compute the derivatives of these functions. We're going to talk about how these derivatives are taken when these functions occur in more complicated functions, and that's it. Other than that, we'll focus quite a bit on where these derivatives are coming from. Some of that, of course, is not going to be tested probably in your calculus tests, but it's good to know where these things are coming from, and it turns out that the derivations of these derivatives are also good practice in rules about limits as well as rules about calculus about derivatives that we have seen so far. Well, let's get to it. We actually, as we take the derivatives of the trigonometric functions, we have to start out talking about two limits that are related to the sine and the cosine function. And before we get to that, we need to prove an inequality, which is that the sine of theta is less than or equal than theta, which is in turn less than or equal than the tangent of theta, for theta between 0 and pi halves to be absolutely precise about that. Now that looks horribly abstract, but this is the kind of inequality that every so often you will need in a physics class, for example, for certain kinds of estimates. And the geometric derivation that we're going to see on this panel somewhat has a physics type feel to it, because you have to draw the picture, do some auxiliary lines, put in some angles, and then get the inequality out of that picture, which is very similar to what you sometimes have to do in a physics problem, say in a force balance diagram or so, where you just have to draw some auxiliary lines to ultimately get some relationships between your vectors. So even though the proof may not have any direct impact on what you're going to do in the future, the idea of the proof is well worth at least seeing once or twice. And so, I mean, just relax, see that you can understand the steps as we go through them, and don't worry too much about us asking you to produce proofs like this on a test. It ultimately will depend on your individual teacher, but if you're taking this class with me, then no, this would not be a regular test problem. Okay, well, let's take a look at this. If we are looking at the angle theta, we just put that angle as it's customary in trigonometry in standard position. The angle comes off the x-axis. And if we then want to know the size of theta, well, the angle theta is the length of the arc that is subtended by the angle on a circle of radius 1. So here would be 1. And sine, cosine, tangent are then all defined through this point up here. This point has coordinates x, y. But if this is theta here, then we know that this height y, well, that's the sine of theta, and because this radius of this circle is 1, we have that this length is 1, which means this y here, that's sine theta. Okay, so that already gives us geometrically the fact that sine theta is less than or equal than theta, because this straight line going down is shorter than the hypotenuse of the triangle that is made up of this point, this base point, and the point here that is marked with the 1. And that hypotenuse, in turn, is shorter than this curved arch, which is, of course, longer than the direct connection, which would be the hypotenuse. So that already gives us that sine theta is smaller or equal than theta. How can we get the tangent? Well, the tangent is opposite over adjacent, right? And so now this length is 1, which means this height here is the tangent of theta. And again, just by looking at the picture, you could say, well, that ought to be longer than this curve of length theta here. If you want to be exact about it, you draw a line vertical to this one at xy that hits this vertical line here, and you realize now that this line plus this line is longer than theta itself, because theta is closer to the straight line connection than these two line segments. And this line segment up here, being the hypotenuse of the right triangle that is made up of these three sides, is longer than this line segment, which means this line segment with this plus this line segment, which is tangent theta, is larger than theta. And so, yeah, there's the point P, and well, tangent theta is smaller or equal than tangent theta. What can we get out of that, or how can we also visualize that? And another way, and again, this connects to things that you may well see in physics classes as well as engineering classes or science classes. Pictorially, if we look at the graphs, we can see that the sine is less than or equal than x is less than or equal than tangent x for x between 0 and pi over 2 ultimately. So that again reflects this inequality, and this picture is something to be kept in mind, because every so often in an applied class people also pull out the fact that for small angles, sine theta, tangent theta, and theta itself are approximately equal. We can see that here by all these three graphs being approximately the same near the origin. So this is a picture that is well worth keeping in mind. We now will use this inequality to prove that the limit of sine theta over theta as theta goes to 0 is equal to 1. How do we do that? Well, 1 is obviously, after we have these inequalities, greater or equal than sine theta over theta, right? You just divide this thing by theta and you're good. Now, sine theta is y, right? So this is y over theta. And now we have theta smaller or equal than tangent theta, which means that y over theta is greater or equal than y over tangent theta. That's because when you go to the reciprocal, the inequality flips. And tangent of theta, well, tangent of theta, if we now go back to the smaller triangle here, tangent of theta is also equal to y over x. So this is equal to y over x. And that's equal to x. And now x will approach 1 as theta goes to 0, because as this angle gets smaller, this point xy will approach this point here, and so x approaches 1. And what that tells us is that the limit as theta goes to 0 of sine theta over theta is equal to 1. Okay, right here you may rightly think, well, how do people come up with this stuff? Why do I need this stuff? Well, we need it to derive the derivatives of the sine function and the cosine function, as is typical for many mathematical proofs that are presented in very linear fashion, because you want to first establish what you use and then use it. You see why you need certain things after you have proved them, because that's when you start using them. We're about to hit upon that. Now again, the reminder here, unless you are in a very demanding class like an honors class or so, this kind of stuff is something that I probably would not test. It is just something, if you can get to the point where you can follow this presentation and at least verify that every step that I've presented here is correct, that is already a very good first step. Picking up the ability to do proofs is very hard. It takes quite a long time, and well, if you really are interested in this stuff, become a math major. We'll certainly be happy to have you. Be that as it may, let's now go ahead and state those limits. What we've just seen is that the limit as theta goes to 0 from the right, actually, of sine theta over theta is 1. And because sine theta over theta is an even function, the left limit will also be 1, and that means that the limit as theta goes to 0 of sine theta over theta is 1. Another limit that we will need, and this goes along the lines of trust me, we will see it in a minute, is the limit as theta goes to 0 of 1 minus cosine theta over theta. Well, how do you deal with that? Well, we multiply with the conjugate here, if you will. We multiply with 1 plus cosine theta over 1 plus cosine theta, because that gives us 1 minus cosine squared theta in the numerator, and theta times 1 plus cosine theta in the denominator. 1 minus cosine squared theta, just verify that that works. Dig out all these things that you have learned by Pythagoras. That's sine squared theta over theta times 1 plus cosine theta. And now we're just going to break this thing up, because this is just sine squared theta is sine theta times sine theta. And so I break that up as sine theta times sine theta over theta times 1 over 1 plus cosine theta. And that's another one of those pattern recognition things. I know what the limit of the sine is, I know what the limit of sine theta over theta is, and I know what the limit of 1 over 1 plus cosine theta is. Namely, those limits are 0 is the limit of the sine, 1 is the limit of sine theta over theta, and 1/2 is the limit of 1 over 1 plus cosine theta as theta goes to 0. And so that limit ends up being equal to 0. How does this backwards analysis of proofs go? Okay, so let's assume for a minute that we can accept that we need to somehow find the limit of 1 minus cosine theta over theta. You look at that and you realize you can't do anything with that, but you know that if you had a sine in the numerator, things would go rather well. Well, then somehow you darkly remember Pythagoras, and you realize that 1 minus cosine squared is sine squared, and you realize that a plus b times a minus b is a squared minus b squared. So expanding with 1 plus cosine theta then becomes something that feels rather natural after you've done this for a while. And well, that then of course pushes the whole rest through. Once you've got a sine squared in the numerator, you realize, well, the sine squared with the theta gives me something I can deal with. I can deal with the sine by itself, and the 1 plus cosine theta in the denominator is not an issue because that goes to 2 as theta goes to 0. So what I'm trying to tell you here is this kind of thing can be understood. Can be understood. I also understand that it is not everybody's cup of tea. Let's now go to something that is closer to what we have done. Namely, we will compute the derivatives. We will compute the limits of the difference quotients for the derivatives, and then we'll look at some examples. So we have that the limit of sine theta over theta is 1, and we can also graphically see that by just plotting the function, it goes through 1. We have shown that the limit of 1 minus cosine theta over theta is 0, and graphically that also works out when you graph that. So that's another way to just double check that these things are correct. And now we can compute the derivative of the sine function, and yes, we have to bite that old bullet one more time. The derivative of the sine function, if we have nothing else available, and we don't, is computed with the difference quotient limit h goes to 0 sine x plus h minus sine x over h. Now we know that when we work with difference quotients, we always want to sort of multiply out the x plus h. Well, we can't multiply this out, but we have a formula for the sine of a sum of two angles. And so sine of x plus h is sine of x cosine h plus cosine x sine h. So all that trigonometry that we have learned a long time ago is certainly useful, and here's one of the places where it does come in handy. We copy down the negative sine x, we divide by the h, and of course we have to keep the limit as h goes to 0 together here. And now we can see, well, the sine x factors out of this, and a sine h over h is something that we can deal with. So this actually breaks up as the limit as h goes to 0 cosine x sine h divided by h, plus the limit as h goes to 0 sine x cosine h minus sine x divided by h. And now the cosine x can be factored out. That doesn't depend on h. So this is cosine x limit h goes to 0 sine h over h, plus sine x can be factored out. Limit h goes to 0 cosine h minus 1 divided by h. And here really is the point that shows this is why we wanted to compute those weird limits, because we need them in this computation. And the geometry before then, we needed to get this limit worked out right. But now that we have all that, we simply reap the fruits of our labor, and we realize that this is cosine of x times 1 plus sine of x times 0, so that's just cosine x. So that's the derivative of the sine function. We will summarize those one more time. Well, how hard can the derivative of the cosine function be? We could use a similar derivation, and it would be similarly ugly, if you will. But we could also use the chain rule. The derivative of the cosine of x is the derivative of sine of pi halves minus x. So all those co-function identities and the like that you have seen in trigonometry are very useful at this stage of calculus, because now I don't need to expand a cosine of a sum or anything like that. I just have to take a derivative with a chain rule, and here's where proofs and examples really start merging, because this is not just an example of working with the chain rule, right? So that derivative is derivative of the outside, which is cosine x, evaluated at the inside, times the derivative of the inside, which is -1. So we're ending up with cosine of pi halves minus x times -1, which is negative cosine pi halves minus x. And cosine pi halves minus x via a cofunction identity, again, that's just sine of x. So the derivative of the cosine is the negative sine. How do we get the derivative of the tangent function? Well, the tangent is sine x over cosine x, so this is actually an example of using the quotient rule. And, well, how does the quotient rule go? Derivative of the numerator times denominator minus derivative of the denominator times the numerator divided by the square of the denominator, and that's exactly what we have here. Well, that's cosine squared x plus sine squared x divided by cosine squared x, and we remember by Pythagoras, that's 1 over cosine squared x. And even though the derivative is pretty quick, this is another differentiation formula that is certainly well worth remembering. And so if we summarize those derivatives, the derivative of the sine is the cosine, the derivative of the cosine is the negative sine. Be careful there that you make sure that negative sign is in the right place. That's another one of those that often goes wrong on tests. And the derivative of the tangent function is 1 over cosine squared of x. I would consider that worth memorizing too. And here's where we are jumping basically to my opinion. There are 3 more functions that people often talk about or feel obliged to talk about: secant, cosecant, and cotangent. In my opinion, and I really have to emphasize that this is in my opinion, if your teacher wants you to memorize those derivatives, you do it. But basically those functions are so rarely used that I personally don't consider it necessary to memorize their derivatives, because if I need those derivatives, I know secant is 1 over cosine, and I can work that derivative out with the chain rule or the quotient rule. Cosecant is 1 over sine, I can work that derivative out with the chain rule. And cotangent is cosine over sine, and I can work that out with the quotient rule. So those things I typically do not memorize, but opinions really are split. I've talked to quite a few colleagues who would probably agree with that, but there are also colleagues who disagree with that. Okay, so now we're getting to just computing some derivatives, and as I said, we're just going to compute derivatives. We're not going to do any kind of graphing or so. You've seen that often enough now, and part of the idea of calculus is that at some point in time, you've got to pick up pieces and assemble them together by yourself. And so it's another one of those where I don't necessarily do you a favor by showing you again how to assemble these kinds of things to graph stuff. So we're just going to show you here how to take the derivatives, and if you've got more complicated problems on the homework, I'm very confident that you can handle them. Yes, they will take time, but it's just math. We can do it. So let's see examples. Derivative of e to the x cosine x. An exponential times a trig function is something that arises actually quite frequently in applications. Typically, it's a damped exponential, an exponential that decays. Here's one that increases. Well, so be it. It's the derivative of a product, so the derivative would be the derivative of the first factor times the second factor plus the derivative of the second factor times the first factor. E to the x cosine x plus negative sine x times e to the x. And the only thing we can do is we can factor out the exponential to get e to the x cosine x minus sine x, and that's just about it, right? Okay, we can also, of course, stick functions inside each other. Now, this problem is thoroughly artificial. I have never seen an application where I would need a function like that, even though I've seen complicated applications where you need to deal with complicated functions, but this is just a practice problem. So this is, of course, a chain rule. In fact, it's an iterated chain rule. It's a function inside a function here, then the sine 2x is inside the exponential, and the 2x is inside the sine. So the derivative is derivative of the outside function, negative sine of whatever is inside, which is e to the sine 2x, times the derivative of the inside, which is the derivative of e to the sine 2x. The derivative of the exponential function is the exponential function itself. So the derivative of e is e to whatever is inside, which is the sine 2x. And then we still need the derivative of the inside, which is the derivative of sine 2x. Well, the derivative of the sine function is the cosine function of whatever is inside, times the derivative of the inside, which is 2. And I think that one, the only thing I could do is maybe put the 2 out front or so, but that really already is the result. You can see here, this is a problem where a lot of content is literally between the lines, in fact between the symbols, because we applied the chain rule once, twice, and then thrice, right? And so that is something that sometimes can also sneak up on you. Be careful with that. Take your time with the problem, even if it looks fairly simple, and just work it out correctly. Okay, yeah, the only thing I did here was pull the 2 out front. Other than that, there is nothing that simplifies. Finally, one that really literally does sneak up on people, and this is one that's important because squared signs do come up in energy considerations, for example, when you're talking about energy of oscillating systems and the like. And if you then want to find the derivative of that, be very careful because the derivative, this is a chain rule, right? Sine squared is the sine function of x quantity squared. So the derivative would be 2 times what's inside, which is the sine function, times the derivative of the inside, which is the cosine function. So the derivative of sine squared x is 2 sine x cosine x. There's nothing more to do to simplify these things. So in conclusion, what we've seen for derivatives of trigonometric functions is that there are some derivatives that are deceptively simple looking, but we've got to get them right. And if we can do that, no, not if we can do that, when we do that, come on, I mean, there's no doubt. It's just computation. It's just math. You can work that out. So when we do that, things work out nicely. And then when we combine this into problems where you want to find tangent lines of trigonometric functions, tangent lines of squares of trigonometric functions, growth behavior, concavity, and so on and so on, well, you know what to do. You take the derivative and according to these rules, and then you execute the process as we have seen it now several times for finding tangent lines, for finding increasing, decreasing, for concavity, and so on and so on. So I'll let you get to the homework and have fun with it.